Hi, everyone. My name is Takuhiro Kaneko from NTT Corporation. I'd like to introduce our work, MIMO-NeRF, fast neural rendering with multi-input multi-output neural radiance fields. Recently, neural radiance fields, or NeRFs, have gained attention owing to their high fidelity and geometrically consistent novel view synthesis. They achieve this by using a SISO-MLP that maps the 3D position and view direction to the color and volume density in a sample-wise manner. However, this architecture requires the repetitive use of the SISO-MLP, which slows the rendering. To overcome this weakness, we propose multi-input multi-output NeRF, or MIMO-NeRF. Instead of a SISO-MLP, MIMO-NeRF uses a MIMO-MLP that performs mappings in a group-wise manner. This change reduces the number of MLPs running by a factor of the number of samples in a group, and speeds up rendering. Before explaining the details of the proposed method, I'd like to clarify the positioning of this study. Other fast NeRFs can be roughly categorized into two models, a NeRF with sample reduction, and a NeRF with alternative representations. In a NeRF with sample reduction, for example, the number of samples is reduced using a sampling network. In a NeRF with alternative representations, fast representations, such as 3D voxels and vector matrix decomposition, are used instead of MLPs. In both models, a SISO-MLP is still used for rendering color or volume density. Hence, MIMO-NeRF is compatible and complementary to these NeRFs, and there is room to improve the rendering speed by replacing a SISO-MLP with a MIMO-MLP. A notable challenge of training MIMO-NeRF is that each point's color and volume density are not uniquely determined, because they can differ according to the group composition. This leads to some ambiguity, and causes fluctuation artifacts. To solve this problem, we developed self-supervised learning, or SSL. We first reformulate a MIMO-MLP in several ways, and then constrain the reformulated MIMO-MLPs to output the same values. Notably, the training time does not increase significantly compared with the original NeRF, because not only pre-trained models are not required, but also each reformulated MIMO-MLP is faster than the original SISO-MLP. Here are the details of MIMO reformulation. We developed two methods. The first is group shift, in which the groups are shifted. The second is variation reduction, in which variation in each group is reduced. In practice, we use these methods simultaneously, and adjust their configuration so that the training time does not increase vastly. The MIMO objective consists of two losses, a pixel-wise loss, and a 3D consistency loss. The pixel-wise loss is derived from the original NeRF, and encourages the predicted pixels to be close to the ground truth pixels. The 3D consistency loss includes the color 3D consistency loss and alpha 3D consistency loss, and encourages the predicted colors and alpha values to be consistent among the reformulated MIMO-MLPs. Notably, the proposed training is self-supervised learning, therefore, no distillation loss is required for training. Here is an example of experimental results using MIMO-NeRFs with and without SSL. The results indicate that the proposed SSL is useful for alleviating the fluctuation artifacts, and improving image quality. We conducted two experiments to investigate the effectiveness of the proposed model. In the first experiment, we conducted a comprehensive study. We first investigated the benchmark performance by comparing MIMO-NeRF self with NeRF, MIMO-NeRF naive, and MIMO-NeRF distill. Then, we examined the validity of the speed-quality trade-off by comparing MIMO-NeRF self with NeRF with small-size MLP, and NeRF with few samples. Through these experiments, we found that when NP equals 2, MIMO-NeRF self can improve inference speed without degrading image quality, and when NP is larger than 2, MIMO-NeRF self degrades image quality, but achieves better speed-quality trade-off. In the second experiment, we investigated the versatility of MIMO-NeRF by applying it to two representative fast NeRFs. First, we applied MIMO-NeRF to DA-NeRF, a representative NeRF with sample reduction. The results suggest that the increase in the number of samples in a group can be used instead of the reduction in the number of selected samples to obtain a better speed-quality trade-off. Next, we applied MIMO-NeRF to TensorF, a representative NeRF with alternative representations. The results indicate that MIMO-TensorF can improve inference and training speed without negative effects by adequately selecting NP. I'll conclude this presentation. To speed up the rendering of NeRF, we propose MIMO-NeRF, replacing the SISO-MLP with a MIMO-MLP. We have developed novel SSL to alleviate fluctuation artifacts without relying on pre-trained models. The experimental results show that MIMO-NeRF obtains a good speed-quality trade-off with a reasonable training time, and is compatible and complementary to other fast NeRFs. The project page is available online. Please check it if you are interested in our work. Thank you for listening.